after STS-128 and was ferried back to Kennedy Space Center in preparation for this current mission. The majority of the work is prepared the orbiter for flight, occurring in the orbiter processing facility. Here we see technicians removing a gaseous nitrogen tank from the starboard side of the payload bay. As you can see, a crane is lifting the tank out of Discovery's midbody. This work was done for weight savings in preparation for Discovery's next mission, STS-133, slated for September. The orbiter's 3 Space Shuttle main engines are removed and replaced after each flight. Discovery's main engines were removed in early October and installed in early December of last year. Each engine is 14 feet long and 7.5 feet wide and weighs approximately 7,000 pounds. Combined, the 3 main engines provide 375,000 pounds of thrust during liftoff. The yellow piece of equipment that you see here is a modified Heister forklift that we use to remove and install the main engines. Each engine is transported from the Space Shuttle main engine shop to the orbiter processing facility for installation. Installing the engines is a very slow and methodical process of ensuring everything is lined up correctly as the engines are inserted into the aft compartment. Technicians, engineers, safety, and quality personnel closely monitor this critical task. The engines are ignited 6 seconds before liftoff when the fuel, liquid hydrogen, is combined with liquid oxygen. Here we see the removed forward reaction control system at the hypergolic maintenance facility at Kennedy Space Center. During Discovery's previous mission, a thruster in the forward reaction control system did not perform as expected. Therefore, it was necessary to change out that thruster prior to Discovery's next flight. Doing so required removing the forward reaction control system and transporting it to the hypergolic maintenance facility. Once all maintenance activities were completed, the forward reaction control system was carefully transported back to the orbiter processing facility for reinstallation. The yellow component that you see here is a holding fixture used to lift the forward reaction control system. Here we see the front portion of the orbiter where the forward reaction control system is located.
And what does the forward reaction control system do, Stephanie?
It actually works in conjunction with the orbiter maneuvering system in the back of the orbiter to generate thrust for velocity changes and attitude control on orbit and during reentry. Here you see a technician performing a tile repair on the underside of the orbiter. There are approximately 24,000 tiles on the vehicle. Every tile is inspected following each mission and repaired or replaced as required. The day after Christmas, the external tank was delivered by barge to the Kennedy Space Center from the Michoud Assembly Facility in Louisiana. Once on dock, we used the external tank transporter to move the tank off the barge and over to the vehicle assembly building. While the entire offload process takes technicians and engineers approximately 2 hours, the actual travel time is only 10 minutes for the quarter-mile trip. The tank is 154 feet long, 27.5 feet in diameter, and holds over 500,000 gallons of propellant. The function of the external tank is to provide liquid hydrogen and liquid oxygen to the 3 Space Shuttle main engines. The outside of the tank is covered in a polyurethane foam that protects it from extreme temperature variations. Once in the vehicle assembly building, we begin the slow and careful process of lifting the external tank into the vertical position and placing it in the checkout cell. The empty external tank weighs approximately 58,000 pounds and is lifted by massive overhead cranes in the vehicle assembly building.
Stephanie, when the tank is fully loaded, how much does it weigh?
The external tank weighs roughly 1.65 million pounds when fully loaded with liquid hydrogen and oxygen. Here you see the aft bipod struts and the propellant feed lines where the external tank connects to the orbiter's aft. Following standalone inspections and processing of the external tank, it's ready to be lifted out of the checkout cell and into the integration cell where it can be mated to the solid rocket boosters. Transport of this delicate flight hardware requires numerous support personnel to ensure careful and safe maneuvering. The forward tips of the solid rocket boosters can be seen here as the external tank is being lowered into position for mate. The tank is now in its final position, mated to the solid rocket boosters. Once all maintenance and checkout is complete in the orbiter processing facility, Discovery is carefully backed out and transported to the vehicle assembly building. While the distance from the orbiter processing facility to the vehicle assembly building is less than half a mile, the trip takes approximately 30 minutes. During the rollover for STS-131, the crew made an unexpected visit and joined our team in escorting Discovery over to the vehicle assembly building. It was great to have the crew here for such an important processing milestone. Once safely in the vehicle assembly building, we begin the process of lifting the orbiter off the transporter and attaching it to the external tank. A yellow sling is connected to the orbiter so that cranes can lift Discovery and move it into the vertical position. Lifting the 200,000-pound orbiter requires use of a 325-ton crane and a 250-ton crane. Once Discovery is hanging in the vertical position, the smaller of the two cranes is disconnected and the larger crane lifts the orbiter up and over the transom into the integration cell. It takes approximately 12 hours to lift the orbiter and get it into the mate position. Technicians closely monitor the movement of the orbiter and are in radio contact with the crane operators at all times. Here you can see the Space Shuttle main engines with their red protective engine covers that are removed before flight. The completed Space Shuttle vehicle is moved by one of our two crawler transporters. Instead of wheels, the crawler has 8 tracks with 57 cleats per track. Each cleat weighs 1 ton. The crawler weighs 6 million pounds and uses 150 gallons of diesel fuel per mile as it travels down a gravel path out to the launch pad. The crawler is 131 feet long by 114 feet wide, which is comparable in size to the infield of a regulation baseball field. The gravel crawlerway is 130 feet wide, roughly the width of an 8-lane highway. At a speed of less than 1 mile per hour, it takes approximately 8 hours to travel just over 3 miles from the building to Pad A. Discovery was delivered to launch pad in the morning on March 3rd. Once at the launch pad, we spent about a month doing a full system checkout of the tank, boosters, and orbiter in preparation for launch.
You know, one question a lot of people have is why does the left-hand solid rocket booster have a thick black stripe at the top and the right-hand one does not?
That was something I learned just recently myself. The solid rocket boosters actually, once they're expended, they're jettisoned from the external tank and fall into the Atlantic Ocean. We have 2 retrieval ships that recover the boosters and tow them back to the Cape Canaveral Air Force Station. The unique stripe that you mentioned is on the left-hand booster, allowing the 2 retrieval ships to differentiate between the left and the right booster as they descend from the sky and eventually splash down in the ocean. The team that prepares Discovery for flight is the best that there is out there, and I'm very honored to work with each and every one of them. We are all looking forward to the successful launch of 131, and followed by the opportunity to prepare Discovery for her final flight later this year.
That's awesome, Stephanie. It's a wonderful occasion. It's the end of a great process, and it's an incredible